Okay, let's continue with the basic differentiation stuff. Here we have the constant multiple rule. Remember, we just did the power rule in the last video, and in the intro we did talk about several different rules. We did the constant rule, we did the power rule, and now we're going to do the constant multiple rule. And it's a nice easy one. So the theorem box says if f is a differentiable function and c is a real number, then c times f is also differentiable, and d dx, the derivative with respect to x, of our constant c times our function is just the constant times the derivative. And the proof of this, I like to include the proof here in the notes. This is a nice short sweet one. The derivative with respect to x of c times some function, well, we go back to our difference quotient, our limit as delta x approaches 0, and here is where we start to break it up. C times f of x plus delta x minus the original c of f of x all over delta x. Well, we can factor that c out. That constant we can factor outside here, and then in the brackets now is just our plain old difference quotient, and then that c we can factor out in front of the limit, that limit notation. So now we have c times this limit. Well, and that limit is just our definition of a derivative, so it just becomes c times f prime of x. Informally, the constant multiple rule states that constants can be factored out of the differentiation process, even if the constant appears as a denominator or as a fraction. So here's the derivative d dx of c times f of x. Just pull that c out front, and then it's c times your derivative, f prime. And it also works, if you see something like this, here's f of x divided by a constant. It might look kind of intimidating, but that constant in the denominator is just a fraction, 1 over c. So we can even factor that fraction out front, 1 over c times that derivative. Just 1 over c times f prime of x. So let's see what we got here in example 5. Use the constant multiple rule. And they give us a function, and then we're just going to find the derivative to it. So first, let's rewrite this a little bit. This is 2 over x to the first power, which is 2 times x to the negative 1 power. So that's our function, and we want to take the derivative of it. Now, the way they just explained it in that previous slide there with the limit notation, what we'd do is we're going to bracket this off. That's 2 times x to the negative 1, and then we're going to take the derivative. 2 times, when we take the derivative in the brackets, the negative 1 comes down front. Negative 1 times x to 1 power lower. Now that gets dropped down to a negative 2. And we can here do the 2 times negative 1 is negative 2 x to the negative 2, and we'll move that down to the bottom, to the denominator, and make it positive. Negative 2 over x squared. Now here, it's sort of like an extra step. What I like to do is, or you'll get in the habit of it, this negative 1 just comes right down front and gets multiplied by the 2 that's already there. Negative 1 times 2 is negative 2, and then we have our x to 1 power lower. Let's look here at b. F of t is 4t squared over 5. We have a 4t squared up top. The 5 is in the denominator. Just concentrate in on that fraction, those numbers, 4/5. So that becomes 4/5 times t squared. And then we'd take the derivative of t squared. It would be 2t times that 4/5. Or, just bring that exponent down, multiply by the constant that's already there. 4/5 times 2 is 8/5. And then we have our variable t, but now to 1 power lower, t to the first power. And if you wanted to make it look more like what we started with, if you want to put that t up there with the 8, that's fine. 8t over 5 would be an acceptable answer. Okay, clear out a little room here. Letter C. 2 times the square root of x. And remember, the square root of x, that's the square root of x to the first. That's the same thing as x to the half power. So here we have, let me come up here, y equals 2 times x to the half power. And we just want to take that derivative. Y prime equals, bring the exponent down and multiply by what's already there. 2 times a half is 1 x, and now we drop this exponent by 1. 1/2 minus 1 is negative 1/2 power. Oops, that's an ugly 2. So 1x to the negative half power, and let's get rid of that negative exponent. 1 over x to the half power Or if you like the radical form, 1 over the square root of x. Okay. Let's see here, letter D. Ooh, now it's looking a little nastier. 1 over 2 times the third root of x squared. So let's just rewrite that denominator a little bit. Our constant out front is 2, and then the third root of x squared becomes x to the 2/3 power. So we have x to the 2/3, and that is in the denominator. So let's bring that up and make it negative. Here we concentrate on the numbers. 1/2. 1/2 is our coefficient in the front, and then that x to the 2/3 comes up as x to the negative 2/3. So that's our function, y equals, now we take the derivative, y prime equals, bring this exponent down and multiply. So here we're going to have 1/2 times negative 2/3, and then we're going to have our variable x, and then we drop the power by 1. So we're at negative 2/3, and we want to drop it down 1, or 3/3. So that's going to be x to the negative 5/3. And let's make this look a little prettier. So here, when we multiply straight across or cancel on the diagonal, this coefficient is going to be negative 1/3. And then we have x to the negative 5/3. X to the negative 5/3. And to get rid of that negative exponent, we're going to drop it down there with the 3. So we're going to have negative 1 over 3 x to the 5/3 power. And there we go. That was a little more complicated, but we can get it. And that was D. We got one more to go there. E. And for E, we have y equals negative 3/2 x. And the x was up there with the 3, so we can just bring it down here and pass the fraction. So we want to take the derivative of that. Remember, this is x to the first power. So we bring the exponent down. Negative 3/2 times 1 is negative 3/2. And this is our derivative. And then we drop this power by 1. That becomes x to the 0. Well, what is anything to the 0 power? Anything to the 0 power is 1. So our derivative is just negative 3/2. The more of those you do, you'll get in the habit of it. Like if you see y equals 7x to the first, the derivative is just going to be 7 times x to the 0, or 1. 7 times 1. If you see f of x equals 10x, the derivative is 10. That if it's a first power variable, it's sort of just going to get derived off the end of it. It just becomes the coefficient that was in front of the variable. And here at the bottom, the constant multiple rule and the power rule are combined into one rule. The combination rule is, and here we have it, the derivative with respect to x of a constant times x to the n becomes c times n. That's when we bring the exponent down and multiply by the number that's already there, c times n, times the variable x to 1 power lower, the n minus 1 power. And let's see what's going on here in example 6. Using parentheses when differentiating. They give us an original function. They want us to rewrite it and then take the derivative of it and then simplify it down and make it look a little prettier at the end there. So the first one, y equals 5 over 2x to the third. We're going to rewrite that as 5/2 x to the negative third. And let's see if I follow what the book does in here. They're talking about using parentheses when you derive. They sort of want you to parenthesize off that variable and then derive it and simplify it. So if we stick to the way the book does it, you're going to have your 5/2 in the front, and then in the parentheses take your derivative, negative 3 x to the negative 4, and then we simplify. Let's see here, 5/2 times negative 3 is negative 15/2. And then x to the negative 4, well, that x to the negative 4, if we want to get rid of that negative exponent, we would drop it down to the denominator. X to the 4th exclusively in that denominator. Negative 15 over 2x to the 4th. Let's see here. Ooh, this next one. Now we got something in the denominator that we have not seen yet. We have a quantity to the third power, 2x to the third. So what we're going to want to do is expand that out. There is going to be a later rule for dealing with quantities in parentheses raised to powers. You know, your instinct is going to say, well, bring the 3 down front. It'll be 3 times 2x quantity squared. That's not going to give you the right answer. So here, when we're taking the baby steps, we're just going to sort of write that out, FOIL that out, so to speak. So our 5 is in the numerator. 2x quantity to the third is 2x times 2x times 2x, or 8x to the third power. And we can rewrite that, bring that x to the third up and make it negative. So we have 5/8 x to the negative third. And this is still our function y equals. Now we want to derive it. Y prime equals, and let's forget the parentheses here, bring down that exponent, multiply by the coefficient that's there. 5/8 times negative 3 is negative 15/8. And then we drop our exponent by 1. That'll now be x to the negative 4. And we could just plug that in the denominator and get rid of the negative exponent. Negative 15 over 8x to the 4th. And let me clear a little room up here. Letter C. 7 over 3x to the negative 2. Again, be careful when you're moving those exponents with negative exponent, or those variables with negative exponents around. Down here, it's 3x to the negative 2. The negative exponent only goes with the x. That 3 does have its own exponent of 1. So if we rewrite this, it's 7/3 x squared. And that's our y equals. And then we derive it. Y prime equals, well, the 2 comes down and multiplies. 2 times 7/3 is 14/3. And then we drop that power by 1, x to the first power, or just plain old x. And again, if you want to put that x exclusively in the numerator, 14x over 3, I'd take that also. Okay, in the last one now, we got another little twist that we sort of saw in part B, where we have a quantity in parentheses to an exponent. So the first thing I'm going to do is rewrite it and get rid of that negative exponent. So we have a 7, and then we're going to bring up, that's an entire quantity to the negative power. So we're going to multiply that by 3x quantity squared. Okay, again, we can just sort of FOIL this out. 3x times 3x is 9x squared. So we have 7 times 9x squared. And we can multiply the 7 and the 9. That's 63x squared. And this is still our function, our original y equals, we're rewriting it. And now it's all set to take an easy derivative. Y prime equals, multiply down here, 2 times 63 is 126. X to 1 power lower, x to the first. There we go. Now, the sum and difference rules, these are nice, easy ones, because if you are deriving a multi-part polynomial, you can just take the individual pieces, derive them, and either add them or subtracting as you were in the original equation. So, Theorem 2.5, sum and difference rules. The sum or difference of two differentiable functions, f and g, is itself differentiable. Moreover, if the derivative of f plus g, or f minus g, is the sum, or difference, of the derivatives of f and g. So let's see here, we got d dx, we're taking the derivative of two separate functions, an f of x plus a g of x. Well, we can just take the derivatives separately and add them. This f of x becomes f prime of x. We had a plus in between, so it stays plus, and then we take the derivative of g, g prime. And it also works for subtraction. If we're taking the derivative of two things subtracted, we can take the derivative of the first thing and then minus the derivative of the second thing. And this works really easy with these real nice long polynomials. Here we have our first one here, a f of x equals x to the third minus 4x plus 5. Well, we want to take the derivative, f prime of x. And since it's all sums and differences, we can just do it piece by piece. What is the derivative of x to the third? Well, that's 3x squared. Minus. What's the derivative of 4x to the first? Well, that's just minus 4. And then we have our plus 5. What's the derivative of a constant? 0. So the constant just derives off. And there we have 3x squared minus 4. The next one. There we go. G of x equals negative x to the fourth over 2 plus 3x to the third minus 2x. So we want to find the derivative of that, g prime of x equals, well here, this first term, I'm going to just scribble underneath it, that is negative 1/2 x to the fourth. That x to the fourth I sort of just slid off. So when I take the derivative here, 4 times negative 1/2 is negative 2. X to 1 power lower, now we're down to the third power. Our next term is plus 3x to the third. So this will be a plus, and the derivative of 3x to the third is 9x squared. Fix that up a little bit there. And our last term, minus, the derivative of 2x is just 2. That was 2x to the first, it becomes 2x to the 0. And anything to the 0 power is 1. So there is our derivative for part B. And that's probably a good spot to stop this video. We should be able to finish up this section in just one more. So I'll see you then.